Friends from the Field webinar series co-hosted by Blue Hill Heritage Trust and Island Heritage Trust. My name is Jacob from IHT, and I had the pleasure of co-hosting with Chrissy today from Blue Hill Heritage Trust. And I'm going to hand it over to Chrissy for a brief tech tip and what we're going to use today for our technical purposes.
Thank you very much. Hi, everybody. I am very pleased to be standing in for my coworker Lander today. And just a little point of order, when as the talk is going on, please feel free to use the chat box or the Q&A feature to ask questions. We will hold the questions for Paul until the end. And Paul's going to go up to probably, close to 5 o'clock, and then we'll save about 10 minutes at the end for questions. And if you prefer to ask your question live, you can use the raise your hand feature, which is on the bottom bar there, and we can unmute you. Sometimes people will accidentally hit that, so don't worry. You don't have to perform if you accidentally hit that, but feel free to use that and the chat throughout, and we'll get to your questions at the end.
Great, thanks, Chrissy. So with that, I want to formally introduce Paul Andrew Mayewski, the Director and Professor of the Climate Change Institute at the University of Maine. He is an internationally acclaimed glaciologist, climate scientist, and polar explorer. He has led over 60 expeditions to the most remote regions of the planet and has made significant contributions to climate science and that are documented in 500 scientific publications, 2 popular books, and hundreds of major media appearances. Paul, thank you so much for being here today.
Jake, thank you for the introduction. I'll just put the share screen on, and well, thank you to everybody for coming this evening. I'm going to be talking about the Arctic, Maine, and the first abrupt climate change event in the modern era. But before I get to that, I'd just like to say a little bit about our institute. We're one of the oldest multidisciplinary climate research units in the world. And we look at the present climate in a variety of ways. We go back in time in order to be able to find out what's the full range of the climate. And we do this largely to improve predictions for future climate. I'm going to talk about or use all 3 of these time periods, the present, the past, and talk about the future of today. We do a lot of things at our institute. There are 135 people. I'm going to focus really primarily on ice cores and also modern climate data. So let me give you a 2-second primer on ice cores. That's what they look like on the left, recovering one in the Antarctic. And the red dots show you all the places around the world where my teams and I have collected these. Ice core records, if you look at the vertical red bars, those are idealized ice cores, can be collected from places like Antarctica and Greenland. In Greenland, we actually drilled 2 miles down into the glacier. I'll talk about that just a little bit. In the case, we've also worked all over the Antarctic, Himalayas, Tibetan Plateau, and we've collected the highest ice core in the world from a little over 26,000 feet. These ice cores are valuable to us because they tell us about everything that's going on in the atmosphere. Everything from temperature, the amount of precipitation, how strong the biological productivity in the oceans, whether or not marine air enters an area, agricultural activity, volcanoes, deserts, industrial activity, mining, on and on and on. They capture everything. I like to say that ice cores don't lie. They have no reason to. And in effect, these ice cores are telling us about air masses that have been traveling around the world. As you find out, air masses have a lot to do with transporting heat, moisture, and pollutants. This particular visualization done by NASA shows you Saharan dust, the orange making its way right into North America and South America. The green is biomass burning. By the way, these are actual images. They've just been colorized. We can see in the white in the northern part of the world, the movement of polluted air masses, for example, acid rain, and we can see idealized in the Southern Hemisphere, the light blue, which is marine air masses, of course, which exist all over the planet. But this is to give you a feeling for how dynamic the atmosphere is, and how, in fact, by tracking the atmosphere, we can learn, as it turns out, about health, resource depletion, the economy, past catastrophes, and geopolitical implications of climate change. Let me just diverge a little bit more for a couple of minutes, tell you what we've been up to just in the last 2 years, keeping in mind that we haven't gone anywhere since COVID. But in the Peruvian and Chilean Andes, we've been working on water availability. In the background are glaciers, and these are shrinking, which tends to reduce hydroelectric power, agricultural production, obviously all sorts of things. It's critical for these people. In 2019, I led the National Geographic and Rolex expedition to Mount Everest, where our team collected the highest ice core ever, a little bit over 26,000 feet, found out that the ice, even at that elevation, is as a consequence of melting and sublimation, and climate change has in the last 20 years decreased dramatically, and all sorts of pollutants are up there from human activity, both local climbers and also from the distance. We've been working in the Swiss-Italian Alps, looking, believe it or not, at pandemics. Turns out that during the Black Death, when 50% of the European population perished, the levels of lead in the atmosphere went down to almost zero, which tells you that that's what the natural level is. However, in the remainder of the last 2,000 years, lead levels have been relatively high, and of course, very high in the last 150 or so years. This turned out to be a very important piece of information because it tells us that we need even stricter lead legislation. We've also worked on the 1918-19 H1N1 pandemic, which killed 50 million people and impacted 1/3 of the Earth population at the time, 500 million people. And it was related, not entirely, but it was underpinned by a climate anomaly. We've also been working in the Antarctic and the Southern Ocean, looking at climate change, pollution, and all the things you can read up there, because as the glaciers in the Antarctic and everywhere else begin to melt, sea level rises, ocean currents change, and in particular, in the Southern Ocean, it warms, it becomes more acidified, and it has more pollutants, which is dramatically impacting the largest, most productive source of marine food on the planet. And then most recently also, we've been working in southern Greenland. We've worked in Greenland for many years, particularly working on the question of resource depletion related to planned rare earth element mines, what these will do for the local agriculture and the people. So with that idea about what you can do with ice cores in conjunction with an understanding of modern climate, let's now take a look at the Arctic, the Maine, and abrupt climate change. The red arrow shows you the distance between Maine and South Greenland, the last picture I just showed you. And it's pretty clear that there are parts of the Arctic that are closer to us than the western part of our own country. We don't live that far at all from the Arctic, and we have a lot in common with the Arctic. Our communities in places like Maine have been isolated for a long time, as they have throughout much of the Arctic. Obviously, we have more advanced technology and better infrastructure, but like the Arctic, everybody in this state and in the higher latitudes is subject to the impact of nature. Well, in 1989, we collected, as I mentioned earlier, a 2-mile thick ice core in the center of Greenland. And from it, we were able to go back 110,000 years, year by year, and understand all of those things that I talked about a little bit earlier, that I gave you a flavor for. Turned out to be the most continuous, and still is the most continuous and detailed record of climate change. So what would you do with a record like this? Turns out that we made a major discovery. It was assumed, and if you look at the diagram on the left, you can see my pointer. This goes from 0 today to about 110,000 years ago. It was believed that the climate changed very, very slowly. It took thousands of years before things changed. What we found was that temperature and storm patterns could change very, very quickly. In fact, in less than 1 to 5 years, faster than a political cycle. And this means changes in storm patterns, precipitation, temperature, and this can be sustained for decades. We also found out that these abrupt climate change events, times when there was a sudden shift towards, for example, more sea ice in the North Atlantic, or less, or more drought, less, as indicated in the case of sea ice by these drops, are directly related with very fast collapses of some civilization. 4,200 years ago was the collapse of the Mesopotamian Empire, modern day Syria and Iraq. And it completely disappeared because they started their civilization not that far from the desert. They had water. The air masses moved just a few miles away from normally where they were. As a consequence, they lost their moisture, their water source, and that was the end of that civilization. Same thing happened to the Mayan Empire several times, once in AD 900, and then around 1000, because the North Atlantic was relatively mild, not compared to today, but relatively mild, the Norse made their way from Iceland to Greenland. And if you look in the picture in the upper right, they built cathedrals, they started sheep farms, but all of a sudden in AD 1400, within a matter of 5 to 10 years, sea ice suddenly came back again, and the net result was they couldn't be resupplied by European vessels, and as a consequence, they died out. They never adopted the Inuit culture. So by about 2004, in many ways, the first entity that we had a lot of press for about 2 years, I have to say, about abrupt climate change, but many people just assumed it was something that could never happen today. We thought it could. And in 2004, the movie The Day After Tomorrow came out, for those of you who remember it. And this is a time, of course, when within a matter of days, New York City, the entire United States, and North America are covered by a large ice sheet and frozen. Well, they got the speed right, but they obviously went in the wrong direction. In fact, what's happening today, obviously things are getting warmer. And one would ask oneself in 2004, when will it happen again? And where, in fact, will you be? So I want to show you where, in fact, we are. And as it turns out, sea ice is potentially, I call it the greatest seasonal event on the planet. This is sea ice month by month going through its expansion in the Northern Hemisphere winter, opposite in the Southern Hemisphere. So why is it so important that sea ice and snow, for that matter, can move so fast? Because of this, because of what's called polar amplification. When you have white surfaces, sea ice, snow, glacier surfaces, they reflect up to 100% of the incoming solar radiation. As they get darker, they reflect less. And as suddenly they disappear and the ocean is exposed, which is dark, all of a sudden the radiation is absorbed, it heats up the ocean, but guess what? The ocean is much warmer than the ice anyway, and when you release that cap of sea ice and let the heat come out, all of a sudden you get at least a doubling of the heating impact because you've released this heat from the ocean. So polar amplification in extremely sensitive areas, and nothing is more sensitive to warming than our snow and ice areas. What's the context for today? Today, CO2, one of the primary greenhouse gases, but not the only one, there's methane, there's nitrous oxide, water vapor, is 1.5 times higher than it has been for the last 850,000 years. This isn't a guess. This is based on actual data, ice cores from Antarctica that are calibrated, well understood. What's as important, in fact, perhaps even more important, is that the rise in greenhouse gases has been 100 times faster than it has been over the last 850,000 years. So if greenhouse gas rise and trapping of heat is conjecturally just one of the components that could create an abrupt climate change event, we're ripe for an abrupt climate change event because we're increasing the amount of greenhouse gas 100 times faster. And if you wanted to pick a part of the world that was going to be most sensitive, it wouldn't necessarily be the Southern Hemisphere because the Antarctic continent, 1.5 times the size of the United States, has an average ice thickness of about 12,000 feet. So it's a while before that goes, although the edge regions all around Antarctica, particularly in this region of the Antarctic Peninsula, are beginning to decay. And the sea ice that surrounds it certainly has an impact, and it's gone, not gone, but it decreases in the summer season. But nevertheless, you've got a giant ocean that buffers everything that's going on here. If you want to have the biggest effect, you go to the Arctic, where in fact we do not have a continental mass at the North Pole. It's all sea ice. The sea ice is 1 to 3 meters thick, 3 to 9, 10 feet thick. Therefore, it changes in extent from summer to winter. And this is where you can get the greatest impact of polar amplification. If we take a look at world temperatures, and this is all relative to the time period 1979 to 2000. We see the change in world temperature. This is land and ocean began to become much more positive by the 80s, sort of flipped back and forth for a while before it eventually started to really rise in the mid-90s, and we know where we're going. It doesn't mean that every single year is going to be warmer than the last, but clearly we're much higher. It's about 1 degree centigrade higher than it was probably in 1950, which is a pretty big deal. But that doesn't give you the whole story. What you really want is a map that shows you where the heating is, where it isn't. Where it isn't is right down here in the Southern Ocean. As it turns out, because of the atmosphere, because the winds are speeding up around Antarctica, which will become well, I'll explain that a little bit later, but just take my word for it. It actually draws the warm air across the top of the Southern Ocean, bringing up cold air. So, and at the same time, coastal parts of Antarctica are melting. But most importantly, the most dramatic warming is happening in the Arctic, right up here. And this is a comparison of the time period 2005 to 2019 compared to the way it was 1979 to 2004. So this immediately tells us that the heating of the planet is very uneven. What is global warming? Global warming is the entire planet warming, which in general it has, but now, as we're in the initial stages, we're seeing quite a difference, and it's the most sensitive areas that are heating up the most. And in fact, if you take a look at the difference between 1980 and 2016, we have an entirely new ocean appearing that didn't exist before. For hundreds of years, people have tried to go across, sail from one side of the Arctic to the other. They weren't able to do it. It was always hoped that the Northwest Passage would open up. As it turns out now, it's actually the Northeast Passage that's opening up. So that still doesn't tell you about abrupt climate change. I will tell you about it right now. If we take a look in particular at the time period 2007 to 2012, in the eastern Russian Arctic, the mean annual temperature, not just the winters, not just the summers, went up 8 degrees Fahrenheit in 5 years. That's equivalent to a doubling in the length of the summer. Just imagine where you live right now if the length of the summer doubled. It's a big deal. And if you lived in a place that's dominated by sea ice, cold temperatures, all of a sudden your entire world has completely changed. And that's what's happened in the Arctic. And what's even more impressive, which we've determined from ice cores, but I won't bore you with all the details, is that this change, 8 degrees Fahrenheit in 5 years, is equivalent in magnitude and rate to the change, the abrupt change that occurred at the transition between the last vestiges of the Ice Age and modern climate 11,500 years ago. So this is not just yet another event in the last few thousand years. This is a very dramatic change. And from what we understand about abrupt climate change events, it will in fact be sustained. There'll be variability, but we will continue to see this situation maintained. So what's happening? How does the atmosphere have anything to do with sea ice, the rest of the planet? Arctic warming changes the temperature profile, the temperature gradient between the polar regions and the mid latitudes. Obviously, the high latitude the Arctic is cold, the mid-latitudes are relatively warm, but if all of it, and when that happens, when the Arctic is as cold as it normally is, let's say 20 years ago, the winds tend to move pretty much directly west to east. However, under situations in which the temperature gradient is less, meaning you warm the Arctic, the winds no longer move that way and they tend to become very, very irregular. And as they get irregular, cold air can be pushed farther south, warm air can be pushed farther north. We all know what happens when warm and cold air comes together. It creates tremendous instability, storms, you name it. So what are some of the extreme examples of this manifestation? It turns out that since about 2014, there have been more and more days in the middle of winter, which is absolute darkness at the North Pole when it's above freezing. So these are jet stream patterns that look like this, and warm air from the south penetrates its way all the way into the Arctic, giving for a couple of days at a time, and every year, more and more days, temperatures above freezing. And this is being verified by Santa Claus and scientific data. So look at some other extreme events. Let's take the wildfires. They're actually going on in Alaska, or did go on and will start again, and also the wildfires in California. When the jet stream changes its pattern, becoming much more irregularly or embayed, in the case of California, any moisture that's coming off the Pacific is pushed far to the north. By the time it comes back down into California, it's lost most of its precipitation, which leads to drying. And because it's got a much longer route to take, it's traveling much faster. So dry, fast winds and drying conditions are exactly what you need to generate firestorms. And this is the simple explanation for what's happened in the western United States, Alaska, and in fact, the number of fires throughout the Arctic are increasing dramatically as a consequence of this. So let's take a look at an example even closer to today. The cold snap that we had around February 20th. This comes off software that we have in our institute that's publicly available, tells you what's going on today and in the past. And of course, we were in the midst of something that was quite cold, 18 degrees centigrade colder than the 1979 to 2000 norm. But you go into the middle of the Arctic, even into Baffin Bay, it was 20 degrees centigrade warmer. So all of a sudden, instead of having a nice, cool high latitudes and relatively warmer mid to lower latitudes, we have, because of the jet stream, we have these patches of anomalies of very hot records, very cold records, and this is all a consequence of Arctic warming. Greenhouse gas warming can, in fact, produce sustained periods of cold, despite the fact that there is warming. And these are sustained periods of cold because the more embayed the jet stream is, the more slowly it moves westerly around the Northern Hemisphere. So there's another wild card in here, and that wild card is methane. And the frozen ground in the Arctic has a tremendous amount of carbon captured in it. And as the ice melts, as the frozen ground melts, if you dig a hole in parts of the Arctic and throw a match in, these people didn't throw gasoline in here. All they did was throw a match in a place where the methane had been trapped underneath the snow, and you have a fire. So methane, not only because of this fire potential, but far more importantly, methane is 30 to 50 times more effective in in trapping heat than CO2 is. It doesn't last as long in the atmosphere, maybe 50 to 100 years as opposed to hundreds of years, but it has the potential for yet another, perhaps even more dynamic, abrupt climate change event that will cover an even larger area, creating even more instability in climate. So as permafrost melts, this is a model that's being done by several groups under the Intergovernmental Panel on Climate Change, reported by the United Nations. And this shows what Arctic temperatures will look like by about the year 2090 to 2100. This is 5 to 6 degrees centigrade higher than what we have right now. Remember that Paris Climate Accord is hoping for 1.5 to 2 degrees centigrade, and that may happen for the entire planet if we're smart, but not necessarily for the Arctic. And it could happen much, much sooner if the methane is released. So it may not be 2090 to 2100. It could be 2050 to 2060. Will it absolutely happen? We don't know. We don't have a crystal ball, but it's part of thinking about the dynamic range of the future. So let me turn to something else that we did in the Arctic, again with ice cores. To show you how, even if you're not working directly in Maine, which we do, also you can find things that are very important to Maine. And that in 1985, with EPA funding, we went to Greenland and we drilled an ice core. Remember, acid rain in the 1980s was the same story as greenhouse gas warming today. There were people who said, no, acid rain is natural, it has nothing to do with human activity. So EPA gave us funding to go to Greenland because we said that if we go to a place that's downwind from the acid rain and we drill back through time and take a look at the levels of sulfur, which produces sulfuric acid, nitrogen, which produces nitric acid, the two forms of acid rain, that we'll be able to see whether or not it is related to the record of emissions. Well, there are big spikes in sulfate. These come with volcanic activity. And whenever you get a giant volcano, I'll talk about that in a little bit, you actually get a little bit of cooling in the planet. But they pop up out of the background and then they go right back down again, the sulfur levels. As of about 1902, the sulfur levels start to go up and with fossil fuel production, particularly burning of coal. And by around the late 1930s, particularly World War II, the levels of nitric acid go up largely because of emissions from vehicles, and they track exactly what was going on in North America. The most exciting thing, which we discovered when we went back to redrill in about 2010, was that in fact the Clean Air Act had worked. It actually reduced the levels of sulfuric acid. And that's an important message that I'll get back to in a minute, the significance of legislation. Get this out of here. So there are undeniable human impacts. And in this particular case, the rise of greenhouse gases is undeniable. Some people might debate that this warms the planet or not. Nope. 98% of the world's scientists and 195 countries have all agreed that it warms the planet. But in addition, there's been acid rain, toxic metals like lead, organic acid, engineered chemicals that we didn't really know what would do to us, radioactivity from atomic bombs, particulates, and much more. And if you look at the last 5,000 years, which is on the right side, that red box shows you roughly the last 150 years, and all of these things go up. And I only plotted back to 5,000 years because if I had plotted the full length of time for which this 150 years and this chemistry of the atmosphere is an anomaly, I would have had to plot the entire record of Earth history. This is absolutely unsurpassed in Earth history. Why in the world does that matter? It matters because when we take in polluted air, polluted water, it changes our ability to fight disease. It changes our physiology. It changes all sorts of things. So we are evolving very differently in the last 150 years as a consequence of, for example, lead. The more lead that's in the atmosphere, the more it affects your nervous system, and there's a direct correlation between that and the ability to learn. So I've termed this the toxic climate cocktail. This is the last sort of really unpleasant part of the talk in many ways. Well, actually not quite, but it'll go back up again. Don't worry, there is hope. The toxic climate cocktail, because if you take a look at all the stuff that we've done with the atmosphere and the ocean, this has particulates in the atmosphere affect our breathing. Lead and other things, cadmium causes autism in small children. It's one of the causes. Lead leads to Alzheimer's, cancers from various things, ecosystem upheaval from ocean acidification, etc. And of course, warning with vector-borne diseases. These are all things that have magnified dramatically as a consequence of the emissions of the last 100 years. And in fact, the whole issue of climate change is directly related to COVID-19 too. We all understand that COVID-19 is a security issue. It impacts all of us. And it operates like climate change on local to global scales. Like climate change, it impacts human health. Because climate change leads to food security and stress, that makes us less likely to be able to fight against COVID-19 with our bodies, not necessarily vaccines. Obviously, COVID-19 causes stress. Mitigation, fortunately, we're in the process of mitigation for COVID-19. Mitigation for climate change is a lot more complicated. Both have created entirely new norms in the way we understand the world, but it's not quite as obvious with climate change. COVID, it's very obvious. And they provided us with completely different perspectives. Now, the silver lining is now we know we can continue to communicate by Zoom. And the silver lining for COVID-19, of which there are not too many, is the fact that when emissions were shut down, we saw a drop in air pollution, which is directly related to greenhouse gases and greenhouse gas emission. But we can't forget that this is a global problem too, climate change. It affects all of us, and we need to keep actively undertaking ways to mitigate and adapt to it. When you think about air quality, 50 million people, 50 million people have been impacted by COVID. 500,000 people in the United States have died from COVID, and 1 in 10 deaths worldwide are attributed to poor air quality. That's 7 million premature deaths per year. This is a major, major security issue, but we don't notice it because if you don't live in a particularly polluted area, everything is fine, you think. So we've developed software, another set of software called 10 Green that allows you with your zip code to go to any part of the United States, and you look at a number. 10 is good. Nobody gets a 10 because of greenhouse gases. The higher the number, the cleaner it is, the greener the value for particulates, et cetera, everything else, the cleaner it is. And these are the data points from all over the United States. This is beautiful data collected by EPA that we actually have taken and put in an easy way to look at. And this is another way of looking at it. You take all of the numbers, green is really good, red is really bad. And if you needed to decide where you wanted to live, or if you had let's say a job opportunity right there in that red spot versus a job opportunity in Maine, which one would you pick? Assuming you understood that air quality was a serious problem. So let me get back to legislation. There have been a lot of climate and environmental surprises caused by human activity. I won't read through all of them. You can read them yourself, but obviously fossil fuel emissions, ocean acidification. I've mentioned a couple of these others, sea level rise, storms. There are even more than I put on here. So how well have we done with legislation? Here's how well we've done. The red star basically says that we didn't get rid of it, but we really did something powerful. There are above ground testing of nuclear weapons stopped in 1972. However, we still have things like Fukushima and Chernobyl. So there is radioactivity. This radioactive activity tends to localize in groundwater, and it appears in various parts of the country. The ozone holes in the Antarctic, and there actually is one in the Arctic, or a group of them in the Arctic. We did an amazing job as an international community with no carrots and no sticks. The Montreal Protocol basically got people to stop using the chlorofluorocarbons that are so effective in destroying ozone. It takes about 70 years for the ozone hole to heal, but it is slowly but surely doing it. Acid rain, we really stopped the sulfur part in terms of the sulfur part. Greenhouse gases, we're getting better, but we got a long way to go. And air quality, yeah, we have lead legislation, unleaded gasoline, but there's tons more in there. that we don't even have legislation for, that you can actually find if you go to 10 Green for where you live. So there's no doubt that legislation works. And of course, under the last administration, we had tremendous weakening of environmental legislation, and it's disastrous. It takes decades to prove that you actually have a problem. It takes years to go through the policy and the courts to actually get the legislation. And we're really setting ourselves up, if we don't sort of counter that negative approach to legislation, we're setting ourselves up for bad air quality and dramatic increases in health costs. So let's go to Maine now and try to tie the whole thing together. Maine has a very diverse range in climate. It's the equivalent of going from about central Norway down to basically just above Italy. Big range. And over in 2009, we were approached by Governor Baldacci, Climate Change Institute, to write a report about Maine's climate future and basically summarize what's been going on. We updated it in 2015. We updated it particularly with reference to coastal areas in 2019, and in 2020 came up with another update. In the meantime, Governor Mills very fortunately put together the Maine Climate Council, which is not only taking, particularly for their science and technology chapter, taking much of what we did, but it's going even farther than that. It's beginning to talk about how various activities in the state will be impacted and what policies are needed to protect them, what policies are needed in order to keep to reduce our involvement with fossil fuels. And as you probably know, one of the things that came out of this report is that Maine has a good chance of going to net carbon zero because of our forests. If we're careful with them, they absorb about 75 to 80% of the CO2 emissions that we produce. We're a very big state, small population, but nevertheless, we're in great shape. So Maine, the winters have changed between prior to 1934, places like Penobscot Bay froze over fairly regularly. You could drive a car from Camden to Castine. 71 was the last time there was a moderate freeze over. It hasn't really happened since then. And if we take a look at the work that comes from our Maine Climate Futures report, this is roughly the last 100 years of Maine temperature, increase of about 3 degrees Fahrenheit, increase of about 6 inches of precipitation. And if you take a look at how that temperature is distributed, 1900, this is the temperature. By 1966, you begin to see the southern half of the state warming up a bit. And by 2010, you begin to see it much more in the southern part of the state, a little bit in the northern part of the state. This all has to do with the jet stream and how far south it comes and what shape it is. So how do we make predictions for Maine climate? One of the mechanisms is to use climate models, and they're very good. They're not perfect, but they're very good. They're based on understanding the physics of the climate system. And what you see here from 1900 to obviously roughly 2010, 2020 is the real climate in green. The black is actually what the models, if you go back in time and try to reconstruct what happened, it's what the models tell you. They're not perfect, but they do a fairly good job. And as you get up into the right side, where it says RCP 2.6 to 8.5, this shows you the projected changes globally in climate, going up to, under the worst emissions scenarios, 8.5, very high temperatures, under the lowest, and where in fact you even begin to level out with emissions up to about 2.5 degrees centigrade by 2100. But notice that the variability isn't really there, and there aren't any really big jumps. And in fact, there isn't even a really big jump in the model that occurs around 2007 to 2012, because climate models can't predict something that isn't already in existing records for the last 100 years. So you need to go back in time, you need to look at other analogs. But if we continue with these models, which are not perfect, but they are an excellent way of thinking about the future, This is Maine today. Green is cold, red is warmer. This is 2035 to 2054, and this is even far. This is the difference between these two. Basically, coastal temperatures increasing 2 to 2.5 degrees by 2035 to 54, and much of the rest of the state 2.5 to 3 degrees Fahrenheit increase. It's going to have a big impact on the growing season, which of course is good in many ways. It'll also have negative impacts, which we'll talk about. Summers are getting longer. They've increased by about a week in the last few decades, and the winters are getting shorter. Along with that came Lyme tick. When my wife and I moved to Maine from New Hampshire, we were so excited in 2000. New Hampshire was covered with ticks. There were no ticks in Maine. And a few years later, bang, we have ticks. The brown shows you the projected rise in tick distribution going right into northern Maine, not as intensely. And this really all has to do with what the temperature is. The warmer the temperatures, the longer the ticks last. Look at, for example, illness, admission to hospital as a consequence of heat exposure. It turns out that even today, when the temperature goes up 5 degrees Fahrenheit, there's a doubling in the number of people who go into hospital because of heat exhaustion. A lot of this has to do with where they live, whether or not they can get ventilation, what their age is, etc. But by mid-century, the number of days in which temperatures will go above 95 degrees Fahrenheit will triple. We all know that we've actually gotten close to this in the last few years. It's going to triple in the next 20 to 30 years. So all of a sudden, wow, its impact on hospitalizations because of heat exhaustion is going to be significantly different than it is now. And Maine has an extremely older population. I'm old, we'll just say older, and also a population that is therefore more susceptible to various diseases, making them even more susceptible to temperature differences. By 2035 to 54, precipitation will increase another 6 inches, which is exactly, from the models, this is exactly what took 125 years to occur already. There'll be a northward shift, eventually into more broadleaf. You can see the lighter color are the broadleaf. As we know, the Gulf of Maine is one of the fastest warming parts of the world ocean. It's expected that it will continue to warm. And when the water gets above 68 degrees Fahrenheit, lobster mortality increases. So impacts, of course, on the lobster industry, which has already collapsed in Rhode Island and Massachusetts, and is moving its way farther north. And of course, the lobster fisheries, they understand this. It may not happen in the next 5 years, 10 years, but it's an important thing to prepare for. So let's not just look at climate future based on models. Let's take a look at what happens when you add additional data in here and take, for example, look at blueberries. Turns out that blueberries like warm temperatures, which they'll get as the Gulf of Maine sea surface temperature increases. And the more rain onshore, the better off blueberries do. And there'll be even more rain because as air gets warmer, it transports from the ocean onto the land that much more moisture. So this is good for blueberries. However, during El Nino, and El Nino is the time when the temperature in the Pacific tends to fluctuate up and down. During El Nino, Maine tends to be drier and warmer. And this happened not too long ago in western Maine and parts of New Hampshire. People were carrying water from rivers to their houses. And it's very interesting that if you take a look at the impact of El Ninos, this warming of the Pacific Ocean, which is a way in which the Pacific Ocean is getting rid of the heat that it has absorbed from the atmosphere and is trying to balance out overall warming in the atmosphere, it usually tends to result in this blue, which is a wetter United States. Maine's pretty anomalous in parts of New Hampshire and Vermont because we're drier. Has to do with the jet stream. By 2040, it is likely, because they usually happen every 20 to 30 years, we're overdue for another big volcanic event like Pinatubo, 1991 to 92. And in this instance, the northeastern United States was cooler and drier for 1 to 2 years. Now, it doesn't last more than 1 to 2 years, but it can have a big impact. And if you're a farmer, 1 to 2 years of drought can finish you off. If we take a look at the impact of the Pinatubo volcanic eruption in the Arctic, remember polar amplification. When you cool the Arctic, you do the opposite, and instead of 1 to 2 degree centigrade change, you have a -4 degree centigrade change compared to the rest of much of the planet. So when we think about what the future will look like, this dashed line shows you that very linear look about what's going to happen globally. But for Maine, it shows you that during El Niños, we might have drying. The opposite of El Niño is La Niña. It might become wetter. Volcanic eruption lasting possibly a year or two like Pinatubo, it'll be drier. And if that methane begins to increase, we're going to have another abrupt climate change event. So thinking about Maine, the world in general, as just gradually warming isn't really enough. We need to be prepared to understand what's going to happen in the next few years, the next 20 years, 30 years. And the plausible scenarios are a much broader range than, So where's Maine in all of this? In terms of natural resources, we're in great shape. We have, other than El Niños and volcanoes, we have a lot of water, which is fantastic. We have forests that sequester 75% of our carbon emissions if we manage them correctly. And we have a marine resource that has depleted dramatically in the last few decades, but we're being smart between aquaculture, seaweed, looking for different species, and studying what it is we need to have a sustained marine ecosystem. Well managed, Maine's in great shape. We have, in many places, solar power. We have the opportunity of offshore wind power. The projected offshore wind power is going to be the equivalent of 10 to 12 nuclear power plants, except it won't explode. It has no radioactive problems. It has some ecosystem issues, but my feeling is for the hundreds of billions of dollars that are going to be needed to do this, invest a small amount in understanding potential ecosystem impacts, and we can probably put these windmills, of which the University of Maine and my good friend Habib Dagher are heavily involved. It'll give us energy independence. We will become basically the Saudi Arabia of Eastern North America if we do this. It'll reduce pollution. It will, as greenhouse gases continue to warm, the Arctic will open up, and eastern parts of the United States, particularly Portland, which is already investing in transport, in vessel transport and material transport between Maine and Scandinavia, Iceland, will become the equivalent of California in terms of opening gateways for travel. More organic farming. We've got water, relatively clean air, a lot of land, and relatively good soil because we haven't depleted it as much. The economy will improve and we'll have much better jobs. The solar industry already employs more people than the coal industry, and these are jobs that aren't going to go away. Wind and solar will continue. When the wind stops, we won't have to worry about climate change. We'll have a much bigger problem because the Earth is no longer rotating. So we're going to get great jobs, and people who might be displaced from some of the current marine activities, they're exactly the people who are needed to be maintaining this offshore winds. They have all the experience about how to function out in the ocean. We will have, and I've said this for quite a while, I think we'll see a doubling in the population in Maine. We're already seeing an increase in population because of COVID-19, but when you look at all of the reasons why it's worth coming to Maine, everything from house prices, although they've increased, to a relatively clean air, water, small population, on, this is a very popular place to live. And as a consequence, quality of life, health and wealth, the two things that we care most about after our families probably will be even better in Maine. So, you know, it's not that Maine, we're going to have vector-borne diseases increasing. We will have storms. We will have sea level rise, but this is all relative. We become an extremely, along with Atlantic Canada, extremely attractive place to move. So we need to prepare for the increase in population. So what can we all do to make to make this happen, meaning adapt to mitigate climate change and even look for opportunities. Well, for one thing, with Governor Mills's Maine Climate Council, we have a science-based approach to all of these things and a significantly more understanding than we had before. If you go to our website, you'll see Climate Reanalyzer, where you can actually teach yourself about climate change, and 10 Green, where you can understand air quality distribution. We need to energize our legislators. Many of them are, but many more need to be educated about what's going on and what we expect for the future, and we need to vote. We need to support climate-friendly activities. That's conservation groups like our host, and various other climate and environmental groups that are in Maine, around the world in general. We need to adopt climate-friendly solutions, and these don't necessarily have to require a lot or even much money. Increased efficiency, reduce our emissions. We reduce our emissions by insulating our houses. There are many grassroots organizations in the state, in particular, I know some right around here that are helping people put plastic on their windows for the winter. 10% of the average Mainer's salary goes to energy. We can reduce that dramatically. And we need to reduce waste and reuse. So we need to insist on clean air, clean water, and we need to be careful about preserving our resources, obviously our natural habitats. So I'll leave you with this quote. Thank you so much.
Thank you, Paul. That was awesome.
Yeah,
I'm always impressed by how much I can learn in just 1 hour by these.
I know.
That was so impressive. Thank you, and well organized, may I say. We do have some questions in the chat box, which I've kind of, I think you may have answered them, but I'm going to ask them anyways, just in case there's more to elaborate on. I'll start with, let's see. With greater climate variability, will Maine have a greater drought-induced forest fire risk?
That's an excellent question. Yes, possibly. As we all know, we've had big fires in this state on MDI. I think 1947, much of MDI was wiped out. And the whole series of human reasons, aside from greenhouse gas warming, but we are at risk in the state of Maine. As long as it stays wet, we do well. But there are times when it can be drier. And thus far, it's primarily been in the western part of the state. That doesn't mean it can't spread. So we need to be very careful. Obviously, we build our houses mostly out of wood. When Europeans come to Maine, they're shocked that all the houses are built out of wood. They build them out of stone and brick. But it's worked really well for us. We have houses that are hundreds of years old. We need to be careful about how close we get to vegetation that can be burned. We need to be very careful about, as the electric companies are, about keeping our electric wires safe so that we don't get sparking. But it is a very important thing for us to be not just seriously thinking about, but planning for. Great question.
Yeah. So Doug Cowan was asking, you talked a little bit about the Gulf of Maine warming, and he wanted to know if you could speak to the changes in the Gulf Stream in particular.
Great question, Doug, and hello. I didn't talk about ocean circulation. Wasn't enough time, but long ago when we discovered abrupt climate change, until we realized the involvement of the atmosphere, it was assumed that abrupt climate change was largely controlled by what goes on with ocean circulation in the North Atlantic. Now, the Gulf Stream, which goes from the western, it comes up the east coast of the United States, then just south of Cape Cod, it goes from us right across into basically northern Europe. And it transports an immense amount of heat because it's coming from the south. Once it gets to the high north, the water is saltier. because the winds in the equatorial regions blow from east to west, and basically they carry moisture out of the Atlantic, leaving more salt in the Atlantic. And so because of the fact that the water is cold, by the time it gets to the North Atlantic and dense with salt, it drops. And as it drops, it actually drives the Gulf Stream to go from west to east, transporting heat. How do you change that? We know in the past that it can change if you add fresh water, because it makes it less dense. The less dense, the less it actually pulls that surface warm water, and the less warm air gets over to Scandinavia. Scandinavia could actually cool if the Gulf Stream slowed down. Why would more fresh water get in? Because of melting of the Greenland ice sheet. And the Greenland ice sheet is melting. And for the last 10 or 20 years, people have been tracking the Gulf Stream, but it's non-trivial because it's not just a river in the ocean. It's a whole series of eddies around the currents. But under the situation in which enough fresh water gets in there, it will slow down the Gulf Stream, and it will change the distribution of heat. So we could very well be going into an extremely irregular, unstable atmosphere, and then bang, all of a sudden, because of even more melting of the Greenland ice sheet, we make it even more complicated by not transporting heat to Europe. Great question. Thanks,
Interesting.
Doug.
Thanks, Paul. Chrissy, do we have any hands raised?
I don't see any.
Oh, okay. All right. So, Paul, again, if you answered this, I apologize, but I'm going to go through them all as most we can before time is over. As the permafrost thaws, both CO2 and methane are released, which will have a greater impact on the surface warming in the next 100 years.
Very important question. Both CO2 and methane have risen dramatically in the last 100 years. CO2 by about 1.5 times. Methane in some cases almost doubled. And we tend to talk less about methane than CO2 because CO2 is much easier to, we know where the CO2 comes from. It comes from fossil fuel burning, and we can actually calculate the emissions. Methane's more complicated. It comes from things like rice paddies, places where you grow within a water environment. It comes from the rear end of cows, a lot of methane, so the more cattle we have. But, that's all moderately well understood. Now, I should say fairly well understood. All of a sudden, there's this tremendous source of methane and CO2, but methane is even more important, coming out of the permafrost. Hundreds of thousands of years, certainly tens of thousands, but probably hundreds of thousands of years of things dying in the Arctic and building up organic material. And methane's about 30 to 50 times more effective in trapping heat. But as noted earlier, its residence time, the amount of time it stays in the atmosphere before it gets back into the land and the ocean, is on the order of 50 to 100 years. CO2 is longer. So the effect of methane will be a fast, abrupt climate change that'll dampen out in a matter of decades unless the methane continues to be released, which it no doubt will. So there's a lot of permafrost. And in fact, going back to I think the 1970s, the Soviet Union always wanted to have a northern Arctic port that they could access year round, which they can now, but couldn't for a long, long time. It was part of the reason for Russia even making its way right down into Afghanistan long before the Soviet-Afghanistan war to get through to basically to India to have an open ocean port. So there was some discussion that the Soviet Union would actually set off atomic bombs in the deep ocean, because in the deep ocean there are tremendous plugs of methane gas that can be released. And one of my colleagues in the institute, Dan Belknap, now retired, lives in southern Maine, spent a lot of time studying methane bulges in the Gulf of Maine. We have methane bulges, places where it's built up. When these get punctured, they release methane. The Arctic permafrost has even more. So it's a real sort of white elephant in the room. It's not included in the models because the assumption was, until the methane release, until the Arctic started to melt so fast, was that it would be sort of background stuff. And all of the estimates actually were underestimates of how much is being emitted now that they're measuring, and they're seeing more and more. And it's just like the collapse of summer sea ice in the Arctic. In about 2005, people realized that the Arctic sea ice would decrease dramatically in the summer. The estimate was 2040 that would happen. Then the estimate was 2025. And then in around 2010 or 12, it was 2015, and it actually was already starting to happen. It's really hard to tell something, to predict something that you've never actually measured before. And even if it came from our records, from past records, it's not necessarily easy to incorporate that into a model. Now that we've seen this abrupt climate change and understand that actually was a precursor for it, had we known how to look for this precursor, we would have done a better job of predicting it. But of course, had we not known that it existed before, we wouldn't have even been able to predict it, or even assume it might happen.
Fascinating. So June has, as a question, sort of followed up with a little bit of a comment and concern, which is going back to the idea of wind farms. She's wondering about the time frame for wind farms in the ocean to really come on board in any real meaningful way, and wondering why we're putting so much energy into things like the CMP corridor and cutting down carbon capture forests when we could be really putting all of our energy into that.
That's a very important question, a very obvious question, and the answer is we shouldn't be waiting this long. Part of the answer is that the systems that are being suggested that are most effective, the offshore systems, which will have the most sustained winds, be far away from people, they have an impact on fisheries depending on where they're put, and that's why the fishing industry needs to be working with determining where these will be. And obviously there are some ecosystem birds and migrating fish. But the bottom line is that it will take a while, and it was greatly postponed by the previous administration, for one thing, in the state of Maine. I think the current administration is clearly much more in favor of it, which is a big help. But also, windmills that far offshore were really quite a pioneering idea. There are windmills directly offshore. You fly into Copenhagen and you fly right along them as you're coming in, but they're not far from shore. And to put them as far offshore as is being suggested for the Gulf of Maine, it requires a lot of testing. It requires new materials. These are all being done, and it requires big investors. If a big investor came along and came up with the money, yeah, you could probably have it in 10 years. But the overall transition to much more renewable energy than we have now is going to take a while. And the infrastructure that we currently live with needs to be maintained. The big question is, should we completely rebuild our old infrastructure? As of the 50s and 60s and 70s, the United States had the best energy infrastructure in the world. It's old now. And we know that we now know much more, and we know that there are different ways and cleaner ways of doing things. So we need to have good federal incentives for doing this. People need to understand that there are more and better jobs in the renewable energy, and the Biden administration, in my opinion, is being very smart because they're not just talking about renewable energy, they're talking about jobs too. But it will take a while, and it's unfortunate that it hasn't happened. And in my opinion, it's the best solution for Maine, along with efficiency, reusing, using solar wherever we can in farms or on our roofs. And of course, I don't know if anybody heard recently, but a lot of US manufacturers are thinking, well, many, not a lot, but major truck manufacturers in the US are thinking about having trucks go electric. And of course, there are more and more electric cars. And there comes another big competition with China. China wants to be the world's producer of electric cars. So if we want to compete with China, another way to do it is to be smart enough to realize that electric cars are the future. And they're the biggest emitter in many ways of greenhouse gases.
FedEx just did their big announcement. It's great.
Amazing, amazing.
Yeah.
And I think, wasn't it GM that said that a dramatic increase in the number of electric cars, I think it's GM, that they want to produce. Very impressive.
And Ford was right behind them.
Yeah.
Nothing like a little competition to get things rolling.
Exactly. Yeah.
We do have time for a few more questions. Jake, do you have one pulled right up?
Yeah, I do. And this one's kind of specific to our area too, Chrissy, because it kind of has to do with brown-tailed moths. John was asking about the toxic effects of aerial spray of insecticide in Maine, specifically to kill budworm, brown-tailed moths, and so on and so forth. He was curious about the effects for humans, and the spray in New Brunswick, could the spray in New Brunswick also drift to Maine? And could it also affect the blueberry crop?
Absolutely, yes. And now it sounds as if John probably knows much more about spraying than I do. I'll just tell you the little bit that I do know. I wouldn't want to be sprayed. There are, I realize why people do it, but there are now more and more ways to preserve crops. And my wife and I lived in France for 1 year between 89 and 90, and we were just shocked at how few birds and how there were in France. And we were told by everybody it was because of DDT that was banned, I think, 10 or 20 years earlier. It basically killed off all the insects, and the birds just didn't come back. So yeah, you know, obviously, sometimes it has to be done because we obviously want to eat. It's the same as oil. Yeah, we use oil, and we can't blame ourselves when we use coal, and we have to be proud of all those people who work so hard to produce all these things. But we know better now, and there are better ways to do things.
So another question that came through was about the Pleistocene Park in northern Siberia. Wondering if you think that may have any potential, or if that has the potential to reduce the rate of the permafrost thaw.
Well, yeah, you know, as it turns out, about 70% of the Arctic land is permafrost, and that applies to Russia. About 70% of their land is permafrost, and they're thinking, because they have cities, some of which are being abandoned because of permafrost, because the structures are falling apart, the railways that they were built to get there are falling apart. For that matter, there's an awful lot of effort going into keeping the Alaska pipeline, from leaking because of permafrost moving all of these things. So question is, can geoengineering prevent the permafrost from melting, and can geoengineering counteract CO2 emissions? And while I believe that it's very important to conduct geoengineering research and to try, none of it has worked. And the classic example is putting sulfur into the atmosphere. Yeah, volcanoes, when they emit, they prevent incoming radiation, but that creates acid rain. We did that already by accident. That's not going to work. Capturing CO2 and putting it back into the ground isn't going to work. Just imagine, how many places can you actually be sucking CO2 out of the atmosphere, putting it into the ground, acidifying groundwater, and actually have much of an impact? And one of the suggestions for permafrost is to spray, in some cases, even plastics. Now, plastics are already all over the world, and on our Everest expedition, we actually recovered microplastics almost on the top of Mount Everest. So there are any places that people go, any place the wind blows, there are microplastics. So I think, there are better ways of preserving parks. If you go and visit the buried army in China, they've built giant football field-like arches over these things, and they're beautiful. They're really well done, and you can't, unfortunately, prevent everything from melting, but you can block off areas. And the idea of spraying things to prevent the permafrost from melting, it doesn't make any sense. The Soviet Union also tried years ago because they wanted to get fresh water into the Arctic Ocean, and they had a lot of fresh water in the form of ice and snow in the Arctic. They wanted to get it into the Arctic Ocean to help actually melt the sea ice because the fresh water it changes the thermal balance in the ocean. So they sprinkled coal dust over a lot of snow and glacier areas as a test, because the more black carbon that you have from burning, the darker the surface gets and the more you melt. However, what happens is that eventually, yeah, it increases melting and you get more fresh water out. But as you do that, more and more of this coal dust begins to coalesce, and it eventually gets thick enough so that it forms a blanket, and you've done nothing. So you have no melting. Well, you could do that in the permafrost in localized areas, but you don't want to be spreading coal dust or black carbon all over the permafrost. It's going to have the ecosystem balance in the Arctic is very, very tenuous. If you take a truck and drive it across an area of the permafrost, almost any time of the year, but particularly as it's starting to melt, you will have two streams that follow the tracks of your truck that will be there for years to come. One drive over the permafrost.
Wow, that's fascinating. Well, I apologize for all the folks who put in really excellent questions. We have run out of time, and I'll blame the good work of the Lands Committee of Blue Hill Heritage Trust, but we do have to go before we're booted off on this shared Zoom space. But I will have these questions, and maybe I'll shoot them to Paul in an email, and if he has any quick thoughts, we could post them when we share the video. This was recorded, and so we will be sharing this video out on YouTube for folks who want to watch it again or share it along. Paul, thanks so much. This was really fascinating, really important, and it certainly helps give us conservationists more purpose to our work. So we're really grateful for your research and you sharing your time here.
Yeah, thank you, Chrissy and Jake, and thank you to Blue Hill and Island Heritage Trust for what you do. What you do is very important too. Thank you
so much.
Great. Thanks everybody for joining us. Have a really terrific evening.